When a stellar system forms, and a star forms in the center, it starts to process the material very close into that star. It's going to form new molecules and it's going to destroy a lot of molecules. But comets, they're so far out, and they've formed so far out in this solar nebula or pre-solar nebula, they're not subject to this processing. They actually contain the material that was in the pre-solar nebula before the star ever turned on. And if we're going to understand that chemistry, we need to study comets.
Comets are, roughly speaking, half dust, rock type material and half ices. And of those ices, the bulk is water ice because it's, again, very abundant, and it's where the comets spend most of their time is quite cold, and so the ice condenses.
The dirty snowball analogy is really a pretty good one. It's mainly dust and ice with a minor smattering of molecules in it.
It starts out as just sort of a fuzzy ball if you look at it at night. When it comes to the inner part of the solar system, the sun's heating starts to blow off that gas and dust, and then you get this really spectacular tail on the comet, what we call the coma. We don't really know on comets how their surfaces, how this dust and this gas gets released to make the coma. Are these things mixed together equally? Is it just a jumble? Are they in layers? How porous is it? Is there lots of empty space in there, or is it packed down together?
There's a couple different ways we could find out what a comet is made out of. The easiest way, of course, is just to go there and scoop out material and bring it back. Maybe not. But that has been done before. The Stardust mission through VILD 2 went to a comet, collected material from the cometary tail, and brought it back to the Earth for analysis. And it was in that set of data that we actually detected the first amino acid inside of a comet. Remote observations using radio telescopes is one of the best ways that we have so far of actually detecting molecules in the coma coming off of the cometary nucleus.
We'd like to measure what the gas is and how it varies as a function of where the comet is in its orbit.
We don't start seeing molecular emission in comets until it's actually being blown off of the surface as it gets close to the sun. And it turns out that the OH molecule, in fact, is the first molecule that starts to get blown off the surface. It's very light.
OH is a tracer of water, and most of the gas that is expelled from comets is often water. So it's a good way to estimate how much water is sublimated from comets at different points in their orbit. And GBT is very good in particular because it can observe during the day, which optical observers can't. And during the day, that means that you can observe the comet when it's really close from the sun, so the last days of the comets have been observed by the GBT.
So we use these radio telescopes to find things like hydrogen cyanide, formaldehyde, methanol, ethylene glycol, which is antifreeze, a common household antifreeze. All this material, all this organic material and complex molecules are in the coma of the comet coming off the nucleus, or actually formed in the coma itself. One of the theories is that methanol, which is a common alcohol, comes off the comet nucleus directly, and then once it gets out to a certain radius, once it gets out from the nucleus far enough, radiation from the sun interacts with it and forms formaldehyde. It takes away 2 hydrogen atoms from methanol and forms formaldehyde. So if this theory is correct, the distribution where methanol is compared to formaldehyde should be much different.
The nice thing about ALMA is it's so sensitive that you can map that entire coma very rapidly, so you can see what the time evolution of how these things are, where they are in the coma, how they get broken up by sunlight, what happens to them afterward.
This theory that we have of where molecules are formed, are they coming directly off the nucleus, or are they formed in the coma, can now be answered with ALMA on any comet that is passing through the inner solar system. So the long period comets, the comets are coming in very far out from way beyond the orbit of Pluto, from the Oort cloud coming in for the first time. They are going to contain this really pristine material. Comets that are short period comets, like Comet Encke, that comes around every 5 years or so, that will have a much different chemistry. They've gone through and have been processed the material several times. Can we observe Comet Encke in this period and actually see a chemical difference every single time it comes through? We were never able to do that before, but observations now are routine with ALMA to actually do this. We could observe Comet Encke multiple times and actually look at how the chemistry has changed in that comet over the next 50 years.